demonstrating competence in the Fortinet AD-VPN, you will be able to configure and test Autodiscovery VPN with IBGP, as well as use the IKE real-time debug to troubleshoot AD-VPN problems. In this section, you will learn how to deploy and manage AD-VPN. Why should you use AD-VPN? To find the answer, you will review the most common VPN topologies. One point-to-multipoint topology variation is called hub and spoke. As its name describes, all clients connect through a central hub, similar to the way spokes connect to hubs on wheels. In the example shown on the slide, each client, spoke, is a branch office FortiGate. For any branch office to reach another branch office, its traffic must pass through the hub. One advantage of using this topology is that you can easily manage the VPN configuration and firewall policies. Also, system requirements are minimal for the FortiGate devices that function as branch offices, because each FortiGate must maintain only one tunnel or 2 SAs. In this example, 4 tunnels or 8 security associations SAs are necessary in the hub. A disadvantage of using this topology is that communication between branch offices through headquarters, HQ, is slower than it would be using a direct connection, especially if HQ is physically distant, as it can be for global companies. For example, if your company's HQ is in Brazil, and your company also has offices in Japan and Germany, latency can be significant. Another disadvantage is lack of redundancy. For example, if FortiGate at HQ fails, the VPN fails company-wide. Also, FortiGate at HQ must be more powerful because it handles 4 tunnels simultaneously, or 8 SAs. This slide shows a VPN that has a partial mesh topology. There are 2 types of mesh topologies, partial mesh and full mesh. Partial mesh attempts to compromise, minimizing required resources as well as latency. Partial mesh can be appropriate if communication is not required between every location. This slide shows additional connections between Spoke 1 and Spoke 2 and Spoke 3 and Spoke 4 connections. However, each FortiGate's configuration is still more complex than hub and spoke. Routing, especially, may require extensive planning. This slide shows a VPN that has a full mesh topology. Full mesh connects every location to every other location. Like the previous hub and spoke example, the example on this slide shows only 5 locations. In order to fully interconnect, each FortiGate needs 4 VPN tunnels, or 8 SAs, to the other FortiGate devices. This equals 3 more tunnels for each spoke FortiGate. In total, 10 tunnels are needed. If your company were to expand to 6 locations, it would require 15 tunnels. 7 locations would need 21 tunnels, and so on. You can use the formula N sites equal N-1 divided by 2 to calculate number of tunnels. This topology causes less latency and requires much less HQ bandwidth than hub and spoke. Its disadvantages? Every spoke FortiGate must be more powerful. Additionally, both administration and troubleshooting get more complicated. So, in general, if your company has many locations, hub and spoke will be cheaper but slower than a mesh topology. Mesh topologies place less strain on the central location and can be more fault-tolerant but are also more expensive. AD-VPN was introduced in FortiOS 5.4. It combines the benefits of hub and spoke and full mesh topologies because all the spoke-to-spoke tunnels are dynamically created on demand. After a shortcut tunnel is established between 2 spokes and routing has converged, spoke-to-spoke traffic no longer needs to flow through the hub. AD-VPN provides direct connectivity. AD-VPN supports single or multiple hub architectures. NAT is supported for the on-demand tunnels as long as one of the spokes is not behind NAT. AD-VPN requires the use of a routing protocol. Currently, it supports BGP and RIPv2 RIPNG. It also supports PIM and multicast. Both IPv4 and IPv6 are supported. This slide shows an example of how ADVPN works. An administrator configures IPsec VPNs in multiple FortiGate devices to form VPN hub-and-spoke topologies. In this example, there are two hubs. Hub 1 has 3 spokes. Hub 2 has 2 spokes. There is also a VPN connecting both hubs. The dynamic tunnels between spokes are created on demand. Say that a user in Boston sends traffic to London. Initially, the direct tunnel between Boston and London has not been negotiated. So the first packets from Boston to London are routed through Hub 1 and Hub 2. When Hub 1 receives those packets, it knows that ADVPN is enabled in all the VPNs, all the way to London because of Autodiscovery sender enable settings. So Hub 1 sends an IKE message to Boston informing it that it can try to negotiate a direct connection to London. On receipt of this IKE message, Boston creates a FortiOS specific IKE information message that contains its public IP address, its local subnet, the desired destination subnet, London subnet, and an auto-generated PSK. Alternatively, can also use digital certificate authentication. This IKE message is sent to London through Hub 1 and Hub 2. When London receives the IKE message from Boston, it stores the PSK and replies with another IKE information message that contains London's public IP address. After the reply arrives in Boston, the dynamic tunnel is negotiated between both peers. The negotiation succeeds because London is expecting a connection attempt from Boston's public IP address. You will explore this in greater detail in the next few slides. Now you will examine the IKE messages that are exchanged when an on-demand tunnel is being negotiated. 1. The client behind Spoke 1 generates traffic for devices located on Spoke 2's network. 2. Spoke 1 receives the packet, encrypts it, and sends it to the hub. 3. The hub receives the packet from Spoke 1 and forwards it to Spoke 2. 4. Spoke 2 receives the packet, decrypts it, and forwards it to the destination device. 5. The hub knows that a more direct tunnel option might be available from Spoke 1 to Spoke 2. The hub sends a shortcut offer message to Spoke 1. 6. Spoke 1 acknowledges the shortcut offer by sending a shortcut query to the hub. 7. The hub forwards the shortcut query message to Spoke 2. 8. Spoke 2 acknowledges the shortcut query and sends a shortcut reply to the hub. 9. The hub forwards the shortcut reply to Spoke 1. 10. Spoke 1 and Spoke 2 initiate the tunnel IKE negotiation. As mentioned earlier, ADVPN requires the use of a dynamic routing protocol. In the next slides, you will learn how to configure ADVPN with IBGP. As an example, you will use an IBGP topology made up of one hub with 2 spokes. All the devices are in the AS65100. This slide shows the following ADVPN configuration in the hub. Disable Set, Add, Route to ensure that dynamic routing is used for learning the spoke's protected subnets. Set Tunnel Search to Next Hop to ensure the next hop IP of the route matched by a packet is used to decide into which tunnel the packet must be sent. Disable Set Net Device to ensure FortiGate does not create dynamic interface. You must enable Set Autodiscovery Sender if you want ADVPN. This setting indicates that when IPsec traffic transits the hub, it should send a shortcut offer to the initiator of the traffic to indicate that it could perhaps establish a more direct connection, shortcut. Assign an overlay IP address to the IPsec virtual interface. This is a requirement for having a dynamic routing protocol over IPsec. The overlay IPs of all hub and spoke participants are in the same subnet. For the remote IP, you can use an unused IP from the overlay subnet. You will need to add the appropriate subnet based on the number of hubs and spokes. For the Phase 2 configuration, ensure that quick modes are set to all 0.0.0.0/0.0.0.0. Set a firewall policy to allow the traffic from the spokes to the hub, from the hub to the spokes, and between spokes through the hub. This slide shows the following ADVPN configuration in a spoke. Enable ADVPN with the command Autodiscovery Receiver. Use this command to indicate that this IPsec tunnel wants to participate in an Autodiscovery VPN, that is, receive a shortcut offer. Assign an interface IP, remote IP, and subnet to the IPsec virtual interface. This slide shows the following IBGP configuration in the hub. Configure a BGP neighbor group. All the spokes are part of it. Create a neighbor range with a prefix that includes all the spokes. In this way, you don't need to define each spoke individually as a neighbor. If you are using IBGP for ADVPN, you must configure the hub as a route reflector, so routes learned from one spoke are forwarded to the other spokes. Add the local networks behind the hub to be advertised over BGP. This slide shows the following IBGP configuration in one of the spokes. Configure the hub as a BGP neighbor. Define the internal network that will be advertised over the BGP. If you are configuring ADVPN on FortiManager using the VPN Manager, remember the following. Set the protected networks to all. Use scripts to enable ADVPN in Phase 1. Disable the option Add Route on the hub. Configure IP addresses on the IPsec virtual interfaces. Configure dynamic routing. If you are using IBGP, use a script to enable route reflector on the hub. It is important to know that when creating Phase 1 using a FortiManager VPN console, the Phase 1 name is created with an underscore and a 0. Phase 1 name _0. For example, a Phase 1 named VPN will be created as VPN_0. The configuration of the protected subnet is under all VPN communities. For ADVPN, turn off the Add Route switch under the VPN gateway configuration of the hub. This prevents the hub from adding routes based on IKE negotiations. For that purpose, ADVPN uses a dynamic routing protocol instead. After the tunnels between the hub and the spokes come up, you can run the following commands in the spokes to verify that routing updates are taking place. Get router info BGP network. Get router info routing table all. This slide shows that Spoke 1 learned the routes to the hubs and to the networks of Spoke 2 through BGP. Spoke 2 is currently accessible through the hub. You can specify multiple IP addresses when debugging IKE. This is very useful when debugging ADVPN shortcuts and spoke-to-spoke ADVPN negotiation issues. If you run the IKE real-time debug during the negotiation of an ADVPN tunnel, you will see the exchange of all shortcuts. This slide shows an example of the output of the real-time debug. You can see the Spoke 1 receives an offer from the hub because of the data traffic from Spoke 1 to Spoke 2. Spoke 1 sends a shortcut query to Spoke 2, and the hub receives this shortcut query and forwards it to Spoke 2. In the example shown on this slide, Spoke 2 receives the shortcut query and sends a shortcut reply to Spoke 1. Hub receives the shortcut reply and forwards it to Spoke 1. Finally, Spoke 1 receives the reply message and initiates a shortcut negotiation directly with Spoke 2, and the dynamic tunnel interface is created. Using the Get IPsec Tunnel List command, you can verify which on-demand tunnels are up. It is important to note that on-demand tunnels remain active until their SAs are manually flushed or until they time out. This slide shows the routing table after the on-demand tunnel is up. You can confirm that the network of Spoke 2 is directly accessible using the on-demand tunnel H2S_0_0. This slide shows the objectives that you covered in this lesson.